banana paper. So what it does, so you don't need to fully understand line by line. I can send you the slide later and with explanations. But it uses something called successive halving algorithm as a core algorithm. So basically, it happens at the beginning. It says that I will define a budget. So this is the budget of resources I'm going to use for this round. It has multiple rounds. Okay? For this particular round, I'm going to assign this budget. So using this budget, I'm going to start allocating resources or distributing resources among the different models. Suppose we have this great number of models here, 2 or 3. I'm not going to run an algorithm for successive halving to do this resource allocation. So what does this algorithm do is that at the beginning, it allocates small chunks of resources, the same amount of small chunk resources to all the options, to all the models. And then it calculates using some utility function, reward function, whatever, it calculates at the end of the round who was the best. Okay? Who was the best? Actually, who was the best half? If you have like 10 models, it chooses the best 5. Throws out the last 5, keeps the best 5 on. And then in the next epoch, next more round, it will do the same thing, but now only for those remaining 5 models. So every time it always throws out half. That's why it's called successive halving. It's half the number of candidates every epoch. So at the end of the epoch, it will have 1 candidate. That's a win. And then it runs another round, runs again the whole big group, but now with a different budget. And it has another winner at the end. So every round it has 1 winner. And it chooses all the winners at the end. And then it runs another round on them, and it will choose the best one. Okay? So this is a top K last line. So this is algorithm. But the theory behind this you can see still a bandit like, because it starts pulling the arms, like when you allocate the resources to the models, actually you can pull it out. Okay? So by doing this, they show that actually using hyperbaric algorithms, you're going to get much lower test errors than any of all the targets, like either random or smearment or the grid search-based hyperbaric optimization models. And not only a training, but the testing errors is also very small. So really it's state of the art. And it is principled. So there's a theory behind it. It's not chemistry. You can really rely on the theory. So this is the first application of bandit theory. The second thing is even, I think, nicer. So if you follow machine learning nowadays, the hottest topic, one of the hottest topics is GAN, right? Actually, it's kind of the claim of game theory. I don't believe it's. I don't think it's game theory. Just game. So basically, you have two. If you are not familiar with it, then just few things about it. So it's unsupervised learning in the sense that its goal is to learn the underlying model of the distribution of the data, right? of the system's data. And the way it does this is it has two it has two components, generator and discriminator. So the generator's goal is to try to generate as good data as possible, and the discriminator's goal is to guess whether it was from the true distribution or from the generated distribution. And because both of them are learning over time, ideally they should converge to a very good solution where actually there's no big differences between the true distribution and the generated distribution of data. Okay, so this is the idea behind it, and the way we train both algorithms is by using the stochastic gradient descent. That's just like a normal neural network. Okay? So here's the typical function they want to solve. So this is a typical structures of GANs. And the function they want to use is actually this min-max function. So one guy will want to maximize his utility, another guy wants to minimize his other's utility. So in game theory, this is something called a zero-sum game, right? Because I want to hurt you, and you also want to hurt me, something like this. And the function itself, I don't want to go into the details, but basically it can be anything there. And here's the problem, it can be anything there. So the difficulty of GANs is how to design objective function. Because the biggest challenge of GAN is that it's not stable. It's not stable. So if you change the parameter a little bit, the whole training goes away. That's the first one. Second one, the convergence is not guaranteed. Because the way SGD is working is that, oh, I move a little bit away, then my opponent moves a little bit away, then I move against him, and then he moves against me, so on and so forth. So no guarantee for convergence. And because of this, it's very difficult to train GANs. And this is one of the biggest. And there are other issues that I will talk about, like board collapsing, right? Board collapse. So for example, if you have a distribution with more than one potential options as the output, GAN typically goes to 1. And it forgets about the rest. So let's see how can we tackle all these problems together using a principle away from bandit theory. So, as I already mentioned, this is a zero-sum game. So if this is a zero-sum game, then why not using learning algorithm for each of the bandit learning algorithm for each of the components to let them play and learn against each other. And actually, a group from ETH Zurich, Andreas Krauss, is a very famous guy. And this is his students' work at 2018. So they use a different version of NPL. It's called FTRL, so follow the regularizing leader. So remember, if you follow the curve leader, they add in a noise, right? Random noise to it. Here in this case, we don't add noise, but we add a regularizer term to it to make things sparser. So by using this algorithm, they train both components of the network, and it happens to be that actually it converges to stable point. And this is a very well-known result from learning theory, learning community. And this result gave Yorgos Laskarakis, I think this is his full name, Laskarakis from MIT, the Nevalin Award 2018. So that award is like a Fields Medal for mathematicians, and that's a Fields Medal version for computer scientists. So just won previous year for this type of work. So we proved that actually if both players use bandit type algorithms, that actually they converge very quickly to the stable point. And in this case, stable point is actually quickly, right? So you can use bandit theory to train GANs. This is the good point of it.
So Valiant was co-author, or?
Sorry?
Valiant was co-author, or?
Who?
Leslie Valiant?
No.
No?
No, Valiant is more like a back learning guy, so not this level of line. Okay, so here's an algorithm. Again, I don't think so we need to pay attention to this one. One thing I want to highlight, other type of things doesn't even matter, the full version case. So in practice, it's a little bit more difficult because you have to play around with